Yes, sir.
In the last class, we have discussed about the construction of DC motor. So basically, the construction you have yoke which provides protection, as a protecting cover, okay, and it also provides a path for flux, okay, role reluctance path for flux, okay. Then we have another part, that is a field system, that is a field system which consists of pole, okay, which has two parts, core plus shoe, core plus shoe, and field winding, okay, field windings. You may have more than one field winding, one or two field windings can be there, and it is, this pole is bolted to yoke, okay. So, and these are laminated, okay. Shoe is always laminated, okay. Then we have an armature. So it has a core with slot plus teeth structure. Just one minute. Okay. Slot and teeth structure. It has a winding. Okay. And you have two types of windings, lap and wave winding. Clear? Now, also there is a commutator. Okay. And brush. Okay. Commutator and brush convert this actually for changing polarities of generated or supply EMF. Supply EMF. Okay, supply EMF or generated EMF. If it's a generator, it will be generated EMF. If it's a motor, it is a supply EMF for generator. Okay, so these are there. I'll again redraw that diagram. Sorry. So here there is a yoke. Okay, it is supported and this is a yoke. It is of either cast iron or a steel. Okay, and you have a field system here. So you have shoe, at least even number of holes will be there. This is the basic part, and here you have a winding. Here also you have a winding, and these windings, they are n number of poles, even they are connected in series. Okay, and now they are connected in series. Okay, and only two terminals are brought out. Here there is a why it is happening. So here there is a armature and there is a armature. Okay, and I'll draw this armature. This is armature. So details are like this. I will show you here. You have a core having slot and teeth structure. Slot and teeth structure. Here there is a slot through which hole passes. Okay, through this hole shock passes. Okay, so this is a teeth and this is the slot. In slot you have a winding. Okay, so here I'll be putting windings like this. So this is a coil or a conductor or a winding. Conductor, coil or a winding, whatever you call. Okay, this is there. So this is the structure of armature. And this, why it is happening so. And this is my commutator and brush. Commutator and brush. No commutator and brushes are there. Two brushes are there. Okay. So I will. This is my slot of. This is my armature, and this is my conductor. This conductor is connected with the thick copper bar. So this is my conductor, and this we call as a commutator segment, which is a thick copper strip, commutator segment. Okay, like this you may have, I'll just draw one more so that it becomes clear. So here there is a commutator, that is a thick copper bar connected to armature. Okay, and between these two, this space is covered by mica sheet. So here you have a mica, which they are insulated by mica sheet. So like this, each conductor armature will be connected. So this is my commutator segment. Okay, on this commutator segment, there are brushes.
तो आप थोड़ा बड़ा बड़ा लिख सकते हैं प्लीज. A labeling.
This is armature. Okay. Oh, there is a screen limitation. Otherwise, every time, because it is not easy to remove it, and then I have to first remove the board, connect the pen, and this is electronic.
Zoom it, sir.
Huh?
We can
Yes.
zoom it, sir, by zooming.
You can zoom it on your mobiles or a laptop. You can have zooming provisions there up to 200 at least. Most of the mobiles provide 2 times zooming. Okay, so this is a mica sheet where commutator segments are insulated from each other, and on that we have brushes. So these are the brushes which is put over here. These are the brushes. So you have 2 brushes. Okay, I have not drawn it completely, just 2 segments I have shown it. Okay, so this is a positive brush and negative brush which are connected to DC supply. which are connected to DC supply. Okay. So like this, you will have all this. This is positive brush, this is negative brush. Okay. And these brushes, these are the brushes. Okay. This small one is the brushes and they are of carbon. We are normally using carbon brushes because of some reasons, because they are softer than the copper. That is the reason. And it is easy to replace them. Instead of commutator, if brush gets damaged, it is easy to remove. That is the reason. Clear? So that's why this brushes are there. Okay. So basically it would be appearing like this. This is my armature. This is the shop. So this is my shaft. You know the shaft, it's a circular, normally a diametric circular rod. And this is the shaft which will be passing through this. So this is my armature.
Sir, they are easily removable in commutator.
Huh?
They are easily removable.
No. They are connected permanently. Only brushes are easily removable. Other things are not like so easy. Okay. I will just put another color. So here there is a commutator. So this is my, you can have N. Okay. So this is my commutator. I'll be putting on this. This is commutator. Okay. It's a copper brushes. So this is armature, commutator. And on this you have, oh, I don't know why it is taking like this. So on this we have a brushes like this. We have a brushes on both the side. So it would be appearing like this. So this is a brush. Okay. This may be positive brush and this is negative brush. It can be as per brush. Okay. And this soft, over this you can put a load, mechanical load like fan blades, or it can be electrical pump, water pump. So like this you can do it. Clear? So this is the physically you will find this is circular. All everything is circular like this. So this is the construction of my motor. Now I cannot show everything inside. So inside portion it is here. So every parts I have shown separately. So this is the structure of my reconstruction of my motor. Actually DC motor or DC generator structure is same. Okay, so it can either be operated, at least theoretically. Practically there are some problems. It can act as a generator, it can act as a motor. Clear? Okay, now on the, see, I told you, actually these are the, just 1 minute. Where it is? So this is my field winding. Okay, this is pole core and all those things are there. So I can have more than 1 or 2 windings on the field. So now I'll just draw that system. Okay, so these are my poles, north and south poles. Okay, I'll be, this is one winding, this is another winding. I can have n number of poles, even, but so here I have shown just 2 poles and they are connected in this way. So this is one winding. Okay, I told you, just I will increase the, so some problem. It is not. So this I can increase. These are just, so on the same pole, I can have more windings. So this is one winding. Again, I can have another winding, second winding. So this is my second winding, and I'll be connecting this second winding again in series. So let us say this is AB. There may be this, say, XY. These are the names. Now, if I draw this, now symbolically the motor will be shown like this. Okay, and I have a field winding is like this. So this is armature. You say plus, minus. Normally, these are brush, indicating brush. This is A, and they are marked A in the laboratory, most of the laboratories. Similarly, this is the winding. I have two winding. Okay, so before I go for more number of winding, just I am taking one winding only on the system. Okay, so when I connect, and here there is a DC supply. Okay, so when I connect field winding, I name this as a FF. It may be F1, F2 in some laboratories. So this is here. So when I connect field winding parallel to, or you call it as a shunt, to the armature, then this A is this one. Don't get confused. So these armature terminals are marked as, I can put M just to show that it is a motor. So A. When I connect A to F and A to FF, this one winding, there it will be in shunt. So when field winding is in shunt, I call it as a shunt motor. सर क्लास चल रहा है 12 बजे बंद करता shunt motor. Okay, so when I connect field winding parallel to armature, we call it the shunting means parallel. Shunt connected means parallel. So then shunt point. And when I connect the field winding in series with the armature, we call it as a series motor. Why? And normally shunt field winding will be labeled as FFF. Series field winding will be labeled as Y. Again, it will be connected to DC supply. Clear? So this is there. Now series winding will be thicker because it has to carry the same current as that of armature. Therefore, it is a thick bars, thick copper winding. And shunt field, it has to carry very small current. So the wires or the copper will be thinner compared to this. Okay, compared to series, the shunt field winding will have a thinner conductors, and this series will have a thicker conductors. Now this becomes a series motor. This becomes a series motor. Okay, now when I can connect both the windings, okay, when can I connect both the windings, then it becomes a compound. So now there are, again, depending upon how you connect series and shunt, there are different types. So just one I will show. Okay. So here I will be connecting both winding. So this is F. Okay. So this is a compound machine where both the field windings are connected. Okay. And specifically, to be more precise, it is a short shunt. This is a type of compound motor. Okay. You don't worry because you are not studying the machines in detail. So this is this. So I hope you have understood what is series motor, what is shunt motor, and what is a compound motor. Okay. So these are the three types of a DC motor, out of which only series and shunt will be studied. Clear? Now we have seen the different types. So how
It
the
is
huh?
short shunt
Short
compound motor
shunt?
के नीचे क्या लिखा था? Short shunt.
Actually, short shunt means how you connect the series and shunt field to the armature. Okay? Depending on that, there will be different types again in a compound motor. So just to, actually you need not to worry. I'll just show you one thing that will make it clear. So I have connected shunt winding across the armature, but it is possible, just for understanding. So there is a problem. What is the object to the shunt motor means what? Yes, object means what? What you want to say? I can connect this shunt
Yeah.
field winding here also. Okay, when I do this, instead of this point, if I connect it here, it become my long shunt machine. Okay, so how I put the windings, that will decide whether it is a short shunt or a long shunt machine. Okay, you don't worry about this. Clear? And there was a question, what is the object means what? Hello?
Sir, why we are shunting?
We want different types of motors. You can put it in series, another type you will get. It is not necessary. You want different types of motors. Okay? There is a special purpose of the motors for specific applications that you will learn later. Huh? Understood? That you will learn later. Okay? Why you want different motors, different types of a motor? That is the basic question you want to ask, I think. Okay? So this is about the what can I say, different types of motors. Okay? ये बार this is very bad. After 20 minutes you are joining. Very like. I told you already, you can join any time, but at least 35 minutes class attendance only, then I'll give you the attendance. Now, how the motor works? How the motor work? That is what I want to know from you. Anybody? कुछ मालूम है? How it would be working? Anybody having some knowledge?
By
There is a motor action principle. Hello?
when current goes and there is magnetic field also.
I'm not able to hear you. See, there is one basic principle called as motor action principle. Okay? On that basis, on that principle, all motors work. So, whenever a current carrying conductor is placed in a uniform magnetic field, or just you can just say in a magnetic field, a conductor will experience a force. Okay, this is the basic principle. So what you need,
To give current, sir.
hello, हाँ सर, मैं क्लास में है सर, अंदर बोलोगे. I'm sorry, I have a lot many administrative responsibilities, so I have to handle everything. Anyway, what was the question asked? Hello? Somebody had said something? Anybody? Who was saying something? Something was said.
What to provide, sir.
I'm not able to hear you. Put your query in a chat. That is better for me. Coil is rotated around a magnet. Yes, coil is rotated around a magnet or around a coil. Magnet is rotated to create a flux. No, that is not there. So basically, this is the motor action principle on which all motors will be working. Clear? So you see here, this is my north pole, okay, and this is south pole, and these are my flux or a field you can call. In this, I'll be putting. I'll take another. So now I'll be having conductor. Okay, this is my conductor. And through this conductor, I will be sending current, of course. Okay, so I will be sending current. Okay, so when I send this current, there is a magnetic field and the current is flowing through the conductor. So this this conductor will experience a force. Okay, so it will, when it experiences a force, it means it starts rotating. Now the direction of rotation is given by Fleming's left hand rule. Left hand rule. So direction of rotation will be given by Fleming's left hand rule. Anybody having the knowledge of this? Can somebody say on this Fleming's left hand rule?
Sir,
Hmm.
it gives us idea about motion, magnetic field, and current, sir. Direction of this.
So, but there is a statement about this. Huh? How will you put in a words? Put it in a word.
Hello, sir.
Huh.
Can I say?
Yes, yes.
When a current carrying conductor is kept in a magnetic field, force applied on it, the direction of force can be determined by using similarity if we moving a conductor in place of magnetic field, sir, and electrical current will be induced in it.
Oh, okay. That is the basic principle. I want to know in which direction your shocks or motor will run. And that is determined by Fleming's left hand rule. Okay. So what is that rule says?
The force is perpendicular to the field and to the direction of current.
नहीं बराबर बताओ you are in the right direction but not clearly. I
So
want
when a current carrying conductor is placed in a magnetic field,
नहीं again you are doing same thing.
Sir, मैं बोलूं?
Wait 1 minute. Durgesh index finger shows the direction of a middle finger shows the direction of a current and thumb shows the direction. Okay, but one point is missing here. Okay, Durgesh has given almost
really perpendicular.
all these will be treated as mutually perpendicular to each other. Clear? Understood? Mutually perpendicular to each other. Then we can say this thing. So direction will be given by flux. Thumb. Okay. So this is what you did. Now, before I move to how actually the torque is generated, I just wanted to tell you one more thing. Now basically, okay, so this you can take as a left hand rule. Now just see if there is a no, say this is my, I'll just tell you, these are my poles, okay? So the flux will move in this line, straight line like this, okay? This is the case when only there is field due to poles, or a main field you can say, clear? Main field you can say, okay? Now, because of the main poles, this is the field generated. Now assume that the poles are not there, only conductor is carrying current. So what will happen? The field will be generated like this. Okay, this is conductor, this is current, and this is my field or a flux. Clear? Understood? How do you get this field? Whenever you know the Oersted law, according to which when current flows through a conductor, when current flows through a conductor, magnetic field is produced. That is the basic law. Okay? That is the basic law. Clear? Okay? So, okay, if here to get this, you have to hold the conductor to know the direction of a field or a flux. What you have to do? You have to apply right hand rule. Okay? So what you have to do? You have to hold the conductor in a right hand, conductor in a right hand, and the thumb in current direction. Okay? Then the fingers, remaining fingers gives the flux direction. Understood? That is a right hand rule. Okay? Also you can have a corkscrew rule to determine it. I hope you know it. Clear? So this is there. Now when in actual systems, current is flowing. In actual systems, the current is flowing. Current is flowing through the conductor as well as flux exists. So initially the main field was like this. Main field. Okay. And now the current field, that is conductor field, exists. Okay. So because of that, what actually happens, this way there is a change. There is a change. This is my conductor and this is my main field. It gets disturbed like this. Okay. So now there is a tendency of the field to regain its original shape. This is original shape. Clear? This is original straight line. Now because of the current flowing in a conductor, there is another field. We can call it as a conductor field. Okay? Or armature field. In simple, conductor in single. So it's an armature field. Okay? So you can call it as an armature. So because of two fields exist in the airspace. In the airspace. So what happens? This main field get disturbed like this or distorted later. Rather it is distorted. Now there is a tendency to regain its original shape like this. Okay. So it tries to regain its original shape. Okay. And in doing so, it exerts a force. In doing so, it exerts a force on the conductor. Okay? It exerts a force on conductor, and that is what we needed. Clear? So this is how now force is applied through some radial distance. So it produces a torque, and that is the rotation. Motor means convert. Now you have converted your electric current or electric energy into rotation, which is a mechanical energy. Clear? Which is a mechanical energy. Understood? So this is how the torque is produced. So when motor action, when working principle is the motor basic working principle is that in a magnetic field you are putting a carrying conductor, it experiences a force and thus rotation is produced. So producing rotation means a motor. Clear? Now, okay. So what in working principle, this is the base and how the torque is generated, that both should be included as a working of the DC motor, not just simple principle. This is Broadway principle. It is applicable to all motors. But in DC motor, how torque is generated, that is explained like this. Clear? Okay?
Okay.
I am repeating. This is the field when there is no current flowing in a only main field. Okay? No armature current or a conductor current. No armature current. Clear? So main field is there. Okay? And this is the field only armature current or armature current, the field produced by armature current. Okay? Only armature current flowing, no flux. This, but in practice both the field exist. Both the field exist simultaneously. So that distorts the main field like this. That distorts the main field. And because of that, the main field tries to regain its original shape like this. And in doing so, it exerts a force on a conductor which produces a rotation. That is what we call as a motor. Okay, that is what we call as a motor. Clear? Understood? So that is the how the torque is generated. So torque generation is like this. Okay. So now next question comes. Now I'll just show this is my pole. I will not show all the details, and this is my conductor or armature. Okay. Armature. This is my pole. Okay. Now it started rotating. What will happen next? Just think about it.
Current will also flow, sir. In opposite direction, I think.
What will happen?
Current will flow in opposite direction.
अरे नहीं ऐसा नहीं होता. See, pole is there, field is passing through that. Current is passing through the conductor. It started rotating. Clear? Current is passing through this conductor armature. This is the main pole flux, and it is rotating now. Now, what does the Faraday's law of electromagnetic induction say? Just recall it. Faraday's law of electromagnetic induction. Okay? What it says, whenever there is a change in flux linkage, EMF will be induced in a conductor. Is it right?
Yes, sir. Yes,
Now,
sir.
here there is a flux, which is a flux due to, or a resultant flux, you can say. So, in this air gap, there is a flux flowing around the armature. In gap between the pole and armature, the flux exists. Clear? And because of the motor action, this conductor is rotating. Is it not? So will not there be a satisfaction? This law is satisfied there. You are rotating a conductor in a magnetic field. So there is a change in flux linkage. You know, in the generation, this is my flux, number of lines. So when I rotate it, at this time this much. Next time it will be like this. Next time it may be 0. Like this, is it not? So flux lines cut by the conductor will be changing. So that means the flux linkage will be changing. So EMF will be induced in a conductor. EMF is induced in a conductor. Okay? And this induced EMF or a generated EMF, we call it as a back EMF. We call it as a back EMF. Why we call it as a back EMF? Because it opposes the applied EMF. So opposition is back. So it opposes applied EMF. What I mean? Here there will be a induced EMF E. Clear? In a motor, there will be induced EMF E which will oppose this applied voltage V. So the voltage under running condition across the armature. So when motor is running, armature voltage will be V minus E. E is always less than V, that you know in a motor, DC motor. So this is there, and the difference is given by IA RA, or you can write V equal to E plus IA RA. Clear? V plus IA RA, where IA is the armature current or a conductor current. You can say simple words. And RA is the, you are putting coil in an armature, so it has its own resistance, and we call it as a armature resistance. Clear? So this is the equation. V equal to E plus IARA. E is the generated EMF, but it is called as back EMF in case of motors. Okay, and that is governed by this rule. Okay, this is just mathematical rearrangement, so don't worry. Clear? Now, how much is the generated EMF? How much is the generated EMF? How it is given? How it is given?
Number of turns into change in flux with respect to time.
Okay, so actually we'll not derive the equation of generated EMF, but I will tell you. So generated EMF or a back EMF, just name given in case of DC motor, is given by the formula. We normally denote this as a EB. It is given by phi Z N by 60 into P by A. Okay, that is the formula. Just wait 1 minute. I write here, that is better. So, okay, so back EMF, normally called as EB, or you can say generated also, it is given by this formula. Phi Zn by 60 into P by A, where phi is the flux per pole in Webers. Flux per pole. You can have n number of poles. Okay, I have shown just 2-pole machine, but you can have 4 poles, 6 poles, and any number of poles. Z is the number of conductors. Number of conductors in armature. Number of armature conductors. And n is the speed at which armature and motor rotates. Speed of motor, and this is assumed to be in revolution per minute. Okay, revolution per minute. Okay, and 60 is a number. Okay, okay, and P is the number of poles. P is the number of poles, and A is the parallel path. Okay, A is the number of parallel paths. Means these conductors, armature conductors, they are connected in series, and there are number of parallel paths. So it is something like this is one path, this is another path, like this. Okay, so just note down one thing. for lap connection, lap type of a winding, P is equal to A. For lap winding, P is equal to A, and this is used for high current machines. Okay? And in the case of wave, which is used for high voltage, okay, this is used for high current. Okay? High current lap is used, and wave winding is used for high voltage outputs. In generator or a motor, you can say input, it will be high voltage input there. Then in that case, A is always equal to 2. A is always equal to 2. Clear? So this is how you can get the back EMF. Okay, so here you stop there. It is very much important. It is, as far as DC motor study is concerned, back EMF is very much important. So I stop here.